All right, so we're going to look at the differential equations of the type found in group 2, where the rate of change is expressed in terms of the dependent variable. So let's take a look at an example first here to see how this kind of works with a basic example. So the graph at the right there is relation. Okay, it's the reflection of parabola in the line y equals x, so it's the inverse of a parabola. So the equation can be shown as x equals y minus 2 all squared. So in this form, when we show it like this, really the independent variable is y, and the dependent variable is x. X depends on what y is. Okay, so let's calculate dx dy at the point 1, 3. So dx dy is 2 times y minus 2. Okay, then dx dy at y equals, that would be y equals 3, will be 2 times 3 minus 2 is 2. Okay, so that's the rate of change of x with respect to y on that graph. Now, another way of showing that graph is y equals plus or minus the root of x plus 2. Based on this equation, the independent variable is y and the dependent is x, which is most commonly what we do. Okay, so now dy dx would be plus or minus 1/2 times x to the negative 1/2, which is 1 over 2 root x. And then dy dx at the point 1, 3. So now our x value is 1. So that's going to be plus or minus 1 over 2 root 1, which is plus or minus 1/2. So two possible values when x is 1. Now we have to look at our graph. When x is 1, there's this point and this point. Okay, so at point 1, 3, we know that the slope is positive. So at point 1, 3, slope is greater than 0. Therefore, dy dx at the point 1, 3 would be positive 1/2. Okay. How do they compare? Well, they're reciprocals of each other. Here, the slope was 2. Here, the slope is 1/2. Okay, here that was for dx dy. Part 2 here was for dy dx. So basically, if we're given a differential equation where it's expressed in terms of the dependent variable, we can take the reciprocal to get the equation, to solve the equation, and then convert it back. Okay, so these are reciprocals. So now, if dy dx equals y, all right, so for that equation, we would go dx dy equals 1 over x. Basically, take that whole equation, take the reciprocal. So then x is going to equal the integral. Oh, sorry, what did I do? Okay, so here we will take the reciprocal of the whole equation. So then x will be the integral of 1 over y, equals 1 over y dy. Sorry, there's not a whole lot of space here. So x equals ln absolute value of y plus c. Okay, then we need to get it back in terms of y equals. So now that will be x minus c was ln absolute value of y. So then y will equal e to the x minus c. Okay. We don't need the absolute value anymore because there's no way e to this x minus c would be negative. So just to summarize here, the rate of change in the dependent variable with respect to the independent variable is related to the dependent variable. Okay, so dy dx equals something in terms of y. So we want to take the reciprocal. So let's look at the first example here. Gardeners are concerned about the spread of a species of beetle. All the specimens detected so far lie within a circular region of radius 25 kilometers. So right now, they lie within that region. And it's suggested that the increase of the radius, r kilometers, might be modeled by a differential equation, dr dt equals something in terms of r. Time denotes time in months. What does this model predict for the radius of the region colonized by the beetle after t months? So in general, after t months. So from here, we want to take the reciprocal. So dt over dr, so the derivative of t with respect to r. So that's root r over 6. So now it's going to be 6 over root r. Okay, so that means t equals the integral of 6 over root r dr. All right, so that's 6. So this is r to the negative 1/2. So the plus 1 is r to the positive 1/2. Divide by 1/2. So t equals, that's really 12 root r plus c. Initial condition, so at t equals 0, the radius is 25. So t equals 0, 12 times root of 25 plus c is 12 times 5 plus c. So c equals negative 60. So therefore your equation is t equals 12 root r minus 60. And then we want to express it. Remember that's dr dt, so we want to express it as r equals. So we need to isolate r. Okay, so then divide by 12 equals root r. Square both sides. So r equals, you can leave it 12 squares, so you could show it as 1 over 144 times t plus 60 squared, or you can expand it out. Okay. Next one. A hot air balloon can reach a maximum height of 1.25 kilometers, and the rate at which it gains height decreases as it climbs. So it goes up really fast, and then it starts slowing down its increase in the height, according to that formula. Okay, so h is height in kilometers, t is time in hours after liftoff. How long does the balloon take to reach a height of 1 kilometer? So we actually have to find a value for this. So we want to take a look at it. This is dh, and it's in terms of h. So let's take the reciprocal. Okay, and then t will equal the integral of that. So you can use substitution, or you can do this in your head. Okay, so t will equal, so dh is negative 1 over 16, so you can show that out front. And this is over, is this set? 1 over 16 du. So that's going to be 1 over u du. And then, substitute back in. Okay. And just remember that we've got absolute value. Your H value is, so remember that H is between 0 and 1.25. So really this is always going to be positive. So if you don't have the absolute value signs, you don't need them. Okay, let's find the initial. So at t equals 0, the height is 0. Okay, it's starting on at ground level. So that's going to be ln of 20. So this is going to be negative ln 20 over 16. Oh, plus c. So c equals positive ln 20 over 16. So then substitute that back in. So t equals, let's see, we have negative, so t equals negative 1 over 16 ln of 20 minus 16h plus ln of 20 over 16. So there's a common denominator. You could show it like that. Really, we're just we're just asked to find out how long the balloon will take to reach a height of 1 kilometer. So it doesn't matter if you don't simplify that further. So we want the time it takes to get to a height of 1 kilometer. So t equals negative 1/16 ln of 20 minus 16 times 1 plus ln of 20 over 16. So that's going to be ln of 4. So really, as one expression, that's ln of 20 minus ln of 4 over 16. And that's the same as ln of 5 over 16. If you simplified it, again, you need to find the decimal answer. We didn't say what to round to, but if you calculate that, you get 0.1005898698695, and that is in hours. So let me just get that out here. So if we have ln of 5 divided by 16, okay, and then we want to probably get it in minutes. It doesn't say here how what to express it in, but since it's part of an hour, I'd multiply it by 60, so it's approximately 6 minutes. Okay, another example, when a ball is dropped from the roof of a tall building, the greatest speed that it can reach, called the terminal speed, is u. So that actually is a value. It's not a variable. One model for its speed v when it has fallen a distance x is given by that differential equation, where c is a positive constant. Find an expression for v in terms of x. So here, this is dv dx. There's your variable, so it's in terms of v. So that's the dependent, so we want to use the reciprocal. Okay, so then x will equal v, so you could bring the c out, 1 over c, and then that's u squared minus v squared. I guess there's two v, I can circle both of them, and that's dv. So I'm going to use substitution here. Now, I've already used u's and v's in it, so let's use a different. So p equals u squared minus v squared, or you can use x. So dp equals u is a constant, so minus 2v dv. So negative 1/2 dp equals v dv. So v dv is negative 1/2 dp. So this, I can factor out the negative 1/2. Put it with the c over p. So that's going to be ln of p. Oh, and I used c here. Really, there's already a c. It's different, so let's use a different constant. Substitute back in. So p is u squared minus v squared. Now, normally absolute value, but u squared minus v squared, if u squared is the terminal velocity, this is always going to be greater than 0 until actually v reaches the terminal velocity. So we don't have to have absolute value signs. Now let's figure out what k is. So at x equals 0, okay, so if you take a look here, x is the distance fallen. So when it just starts, it hasn't fallen at all. The velocity is 0. So we're going to put 0 equals negative 1 over 2c ln of u squared minus 0 squared plus k. And solve for k. So bring that over. That's going to be 1 over 2c ln of u squared. So that's really ln of u squared over 2c. Put it back in. Now, I could use my laws here on this last one. 2 goes in front, the 2's divide out. But I notice that the first term has a denominator of 2c. So actually, it might be easier to leave it in that form, right? So they both have a coefficient of 1 over 2c. And we want to solve for v in terms of x. So where's your v? It's here. All right. So I want to isolate that term. So that's positive. I'm going to bring it to the left. Sorry, that's negative. If I bring it to the left, it's positive. So then that would be 1 over 2c ln of u squared minus x. Okay. So the 2, if I multiply through by 2c, both sides, then those divide out. I get ln, oops, just a sec, get ln of u squared minus v squared equals ln of u squared minus 2cx. And then, now actually, I want to get v squared by itself. But there's 2 terms with ln in them. So if I bring that ln term to the left, then I can show this as 1 logarithm. So that would be ln of u squared minus v squared over u squared equals negative 2cx. And then convert that using exponentials. So that's going to be e to the negative 2cx equals u squared minus v squared over u squared. And now get v by itself, so multiply through by u squared. And then that would be v squared equals u squared minus u squared e to the negative 2cx. Okay, and I'd probably factor out the u squared. and then V, that will equal, now, normally when we solve for a V, we would take the positive or negative root, but V is going to be a positive value. So we'll just take the positive root. So that's u squared 1 minus e to the negative 2cx. So that's going to be equal to u, the root of 1 minus e to the negative 2cx. Okay, so that's V. All right, so another example. This one we're trying to figure out which is the best model. So it says a steel ball is heated to a temperature of 700 degrees Celsius and dropped into a drum of powdered ice. The temperature falls to 500 degrees in 30 seconds. Two models are suggested for the temperature capital T after T seconds. So if one model is the rate of cooling is proportional to the temperature, and the other one is the rate of cooling is proportional to T to the 1.2. It's found that it takes a further 3 minutes for the temperature to fall from 500 to 100 degrees. Which model fits this information best? So let's look at model A. Oops. And so that's saying that the rate of change of the temperature with respect to time is proportional to the temperature. Okay, so then remember, capital T is the dependent here, so we want to take the reciprocal. All right, so that means time is equal, we can factor out the 1 over k because that's not a variable. Okay, so that's your equation. We need to solve for C using our initial value. So at time 0, the temperature is 700. You may need to use some extra paper because this takes up a lot of paper in this one. So 0 equals 1 over k ln of 700 plus C. So C equals negative 1 over k ln of 700. All right, put that back in. And so we get T equals 1 over k ln of T minus 1 over k ln of 700. Now you could simplify this, right? You could factor out the 1 over k. That's ln of T minus ln of 700. So T equals ln of T over 700. Okay. You could keep that all in the absolute value, or leave it like that, absolute value of T, because 700 is just a constant, right? Okay, so that is for model A, and then we can check. We need to find out what K is, right? So in this situation, what is K? So we do know that initial temperature was 700, then it falls to 500 in 30 seconds. So at T equals 30, the temperature is 500. So we need to figure out what K is. So it's going to be 500 over 700, which is 5 over 7. And then actually what you could do here, you could find out what K is, but then it's 1 over. So it actually solve for 1 over K. So that's 1 over K is 30 over ln of 5 over 7. So then therefore T is equal 30 over ln 5 over 7. And then the numerator is, actually, I'm going to keep it separate. It doesn't really matter. And then ln of T over 700. Okay. And then you can find the decimal form of the coefficient if you want. Well, we can just wait until we can test it. Might as well do that now, I guess. So let's now see. This is your Model A. And now let's test it with the information that's given there. It is found that it takes a further 3 minutes for the temperature to fall from 500 to 100. So since the beginning then, you've got 30 seconds plus 60 times 3 is 180. So that's 210 for time, and the temperature ends up being 100. Okay, so we want to see how close this is. So really, if you substitute this in, it might not be equal to each other. So don't put both of them in. Because this is solved for t, let's substitute t equals 100 in and see how close we get to 210. So that would be 100 over 700, which is 1/7. Okay. So get out your calculator. All right, so then let's enter this. So you could go 30, you can go 30 ln 1 divided by 7, because that reduces, close the bracket, divide by ln 5 divided by 7, close that bracket, enter, you get 173.5, which is not close to 210, really. Not close. Okay, so likely the other one is. Let's check it out. So now this one is the capital T, the lowercase t, different K from the last one, obviously. So then we want to take the reciprocal. Okay. You could show that as t to the negative 1.2 if you wanted to. So we'll factor, show the 1 over k out front. And then this is, I'm going to show it as a negative exponent. Okay, so integration, so that's going to be t to the 0.2 over 0.2. Okay, so 0.2 in the denominator is like 5 in the numerator, so that's 5 over k, t to the 0.2 plus c. Then we have our t equals 0, time equals 0, temperature is 700. So 0 equals 5 over k 700 to the 0.2 plus c. So c equals negative 5 over k 700 to the 0.2. Okay. Oh, what did I just do? That should be negative. Sorry, negative 0.2, negative 0.2, negative, 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 and then that's going to be positive. Okay. All right. Oh, sorry. That's going to be, that's still negative, and then here, this is going to be positive. That's where I meant to erase. Okay. So now, we want to substitute that back in. So t equals negative 5 over k, t to the negative 0.2 plus 5 over k times 700 to the negative 0.2. So we could factor out 5 over k, and then we get 700 to the negative 0.2 plus, minus t to the negative 0.2. Okay, so then let's figure out what k is. So we found out what c is. Okay. T equals 30 when temperature is 500. So we've got 30 equals 5 over k, 700 negative 0.2 minus 500 negative 0.2. So really, 5 over k, because we want to put that back in here. Might as well just solve for that. Okay, and then substitute it back in. Right, so 30 over All right, so then let's test this out. So that's your equation in terms of t as an exact form. You can obviously find this value here. Now let's see, when we substitute t equals 100 in, do we get 210, right, for the time? So 30 over minus 100 to the negative 0.2. Okay, so let's get our calculator out. All right, so you might want to use the fraction form if you have, clear that. Alpha y equals, okay, so 30 bracket 700 to the exponent negative 0.2. Just going to move this over here. Minus 100 to the exponent negative 0.2. Close the brackets. Denominator, open the brackets, 700 to the exponent negative 0.2 minus 500 to the exponent negative 0.2. Close the bracket, enter. 205, basically 205.0. We wanted to see, is it close to 210? Pretty close, right? So that's definitely closer, so much closer than Model A. All right. That was really 2 and 1. And last one in group 2. It says, if the rate of growth or decay for a substance is proportional to the present amount of the substance, then the substance is growing or decaying exponentially. The differential equation representing exponential growth or decay k is dq to dt equals a constant times q, where t is the time in appropriate units, c is the constant of proportionality, and q is the present amount. Show that the equation relating t to q is that exponential, where the initial q is the initial amount of the substance. I think I'm going to change this to k. I always use more often k for constant of proportionality. So we are starting with dq, not Dairy Queen, dq equals kq. So now we want to take the reciprocal. Okay, and then t equals the integral. I'll put 1 over k out front. So that's 1 over q dq. So t equals 1 over k ln of q plus c. Q is the initial amount, so we're assuming that's greater than 0, so you don't have to have the absolute values. At t equals 0, our initial amount, so q equals q naught. All right, so substitute that in. So 0 equals 1 over k ln of q naught plus c. So c equals negative 1 over k ln of q naught. So then our equation you can, as I said, you can keep round brackets for that if you want. Now let's factor out 1 over k, and then we'll have subtractions of natural logs. So we can show that as q over q naught. Okay, that's t. Now we want to get q by itself. So that means we want to get this logarithm by itself. So I'm going to multiply both sides by k. And so now that means that q over q naught is e, the base of the log, to kt. And then if we solve for q, we get q naught e to the kt, which is what we were trying to show.